Hello guys, this video will cover contingency table. First, we'll discuss the definitions of a contingency table, and then the steps for creating one. A contingency table is a tabular representation of categorical data. A contingency table usually shows frequencies for particular combinations of values of two discrete random variables, x and y. Each cell in the table represents a mutually exclusive combination of x, y values. In statistics, a contingency table is a type of table in a matrix format that displays the multivariate frequency distribution of the variables, or a table used to classify sample observations according to two or more identifiable characteristics. So here we have the contingency table for the study that was carried out on a number of students, and we record smoking status and gender for each of them. And these just are two categorical variables. Now, just to explain what's going on in our table, we can see that in the right bottom corner, we have the total number of students surveyed. If we move into the center, we can see that 72 students surveyed were male smokers, 44 were male non-smokers, 34 female smokers, and 53 were female non-smokers. 106 of total number surveyed were smokers, 97 were non-smokers, 116 were male, and 87 were female. Along the top, we have two options for a categorical variable, and these are smoker and non-smoker. And then, along the side, we have the two options for second categorical variable, which are male and female. So, the table we have here is called a frequency table because it requires account values for a study. But it's always a good idea to make the data as simple as possible, so that when you look at it, you can tell straight away what's going on. On a table this gives is called a relative frequency contingency table. So to get the percentage value of the particular cell, we divide the count value for that cell by the total number of students surveyed and multiply that by 100. So far, first cell we divide 72, which is our count value for cell 1, by 203, which is the total number of students surveyed, and we get 35.47%. The calculation for the other three cells are exactly the same, and I have the calculations here just so you can see where I am getting the values from. Just have a quick look back at our contingency table. The percentage value for the first cell is found by dividing 72 by 203 multiplying by 100, and we get our percentage value. When we've done this for each cell, we put our new percentage value in the table, and we have our relative frequency contingency table. So here in the bottom right hand corner, we have the 100% instead of 203, which just represent the total number of people surveyed. In the center, we can see that 35.47% of people surveyed were male smokers, 21.67% were male non-smokers, 16.75% were female smokers, and 26.11% were female non-smokers. So now that we have generated our relative frequency contingency table, we could be able to find the joint distribution. So just to be out here at the joint distribution of our two variables is the corresponding percentage in terms of our two record of categorical variables, gender and smoking status. All that means is that we need to find a percentage of corresponding to each combination of our two categorical variables. So in our case, there will be male smoker, male non-smoker, female smoker, and female non-smoker. All we have to do is go back to a relative frequency contingency table and look at the 4 central values, and this is a joint distribution. If we add these 4 values together, we should get 100% because these are the only categories that a person from our study can be classified into. So now that we have our joint distribution, we could be asked to find the marginal distribution from this. So, if we found a joint distribution of our categorical variables and asked to find from this the individual distributions of each categorical variable, then these distributions are called the marginal distribution. From the example, we have just found out a joint distribution, our gender and smoking status. And now we want to find the individual distributions of these. These are a marginal distribution, so we are looking for the marginal distributions of gender and the marginal distribution of smoking status. A way from remembering is if we have the joint distribution and we are going from that to the single distribution of our variables, then we are looking for the marginal distribution. So, define the marginal distribution, we go back to our relative frequency contingency table. The marginal distributions are found in the outer margins of the relative frequency contingency table, which is another good way of remembering how to find them. So, if we look at the last column of our table, we can see that 57.14% of the students were male, and 42.86% of the students were female, regardless of their smoking status. This is our marginal distribution of gender. In the bottom row, we can see that 52.22% of students we surveyed were smokers, while 47.78% were non-smokers, regardless of their gender. And this is the marginal distribution of smoking status. The last thing we might need to find is the conditional distribution. So the conditional distribution is the distribution of one event given that another has occurred. We go back to our example and say we are interested in finding distribution of smoking status for each gender level. Because we are conditioning on gender, we now divide each value by its row total instead of the overall total. So all we do is divide 72 and 44 by 116 and 34 and 53 by 87, and then multiply each value by 100 to get the appropriate percentage. So I've just included the calculations here. When we divide 72 and 44 by 116, we get 62.07% and 37.93% respectively. When we divide 34 and 53 by 87 multiplied by 100, we get 39.08% and 60.92% respectively. We can pop these out values back into the table just to make things a little simpler. And we can see now that our row totals are 100%. This is because we have restricted under. So each row gives us a conditional distributions of smoking status for each level of gender. Similarly, if we interest in the conditional distribution for each level of smoking status, we divide each value by its column total because we are conditioning on smoking status. So again, after the calculation include, and you can see we have divided 72 and 34 by 106, which is our column total, and multiply by 100 and we get 67.92% and 32.08% respectively, and divide 44 and 53 by 97 and multiply by 100 to get 45.63% and 44.64%. Putting these values into a table, we can see that our both column totals are 100% because this time we have restrict smoking status. Now, each column gives us the conditional distribution of gender for each level of smoking status. I'm using data from NBA Players season 2021 to 2022. The collected data from these two websites. Here's the example. Given this table, can you calculate the following metrics? In the table such as this, Notice that there are no numerical values. The person ID is the numerical identifier, but the numbers are arbitrary, so there is no obvious calculations to perform. However, because each row represents one player, we can count the number of rows along each dimension, lineup, and dominant hand, to analyze how the dimensions are distributed. To create a contingency table, the first step is to aggregate the original dataset along the two dimensions, lineup and handedness, and count the number of rows for each combination values. Since there are two possible values for lineup, which is starting and bench, and two possible values for dominant hand, which is left and right. So there are four total possible combinations: starting and right, starting and left, bench and right, bench and left. For each of those combinations, we count the number of rows that contain both values. At this point, we can extract information regarding to the quantity of each combinations, allowing us to answer basic questions such as how many bench players are left-handed, and are there more starting or bench players who are left-handed. Next, we perform a cross-step on the result, moving the dominant hand to the horizontal axis. This will make interpretation of the results much easier and allow us to easily calculate totals along each dimension. There are other questions, however, they are harder to answer, and these deal with the proportions of each combinations. What proportions or percent of starting are left-handed, and are greater proportions of bench left-handed than starting? For those questions, the proportions of lineup, we need to divide the values in the cells by the totals along the lineup axis, which in this case is vertical. The resulting table, called a row conditionally frequency table, will have 100% values in each cell in the total column. The cells for each rows will account for all the players within the category, starting players and bench players, or the lineup dimension. The table can be easily read. 90% of starting players are right-handed, and only 6.53% bench players are left-handed. But what if we want to know what percent of left-handed players are bench players? This is a different type of question, one that can be answered by dividing the original values of the cells by the totals along dominant hand, or horizontal axis of the contingency table. These are called a column relative frequencies. Now, the result can be interpreted into sentences by focusing on the columns in the contingency table. 33.16% right-handed players are starting, and 55.89% left-handed players are bench. But what if we want to answer questions about how prevalent a separate combination is among all the players in this dataset? For instance, what percent of the players are left-handed starting? For that, we divide the original values by the total of rows in the dataset. As you guys can see, with this table, we can answer many basic questions about dataset, including what percent of players in this dataset are right-handed? What percent of the players in these datasets are bench? What percent of the players in these datasets are left-handed bench? And so on. Note that the language we use, what percent of players in this dataset, is different from easier to say, what percent of players. This is because the datasets being used is a sample of population, and to infer the trends about the population, we will need to use a statistical technique. Okay, that's all for the contingency table. I hope you guys understand. Thank you.